Welcome back to the Linear Regression Part 2 lecture, guys. Let's start from the point where we left in the previous lecture. I'm excited here because we are going to create our first model here. Now we have features in X and target in Y, which is price. The next step is to split the data into training set, which is X train and Y train, and the testing set, which is usually X test and Y test. We will train our model on the training dataset in X train and Y train, and then use the test dataset in X test and Y test to evaluate the model. Scikit-learn already has a method train_test_split to do this task. Let's import that model first. From Scikit-learn, and this is a part of model selection. So dot model selection import train test split. Remember, you can always use tab for autocomplete. Let's run this cell. Now we have imported train test split. We will pass our test train data to train test split and tell the test size, which is the percentage of data set that we want in the test set. Let's check train test split, press Shift Tab, and if we explore and move down, we see this code. Let's copy this code so that we can save some typing. So paste it here, delete these dots, and here we have. Let's split this into two lines here. So what train test split is doing, it's taking X and Y, where X is data frame with all the features that we have selected, Y is the target values, and splitting that into X train, X test, Y train, and Y test. It's taking the test size 33%, which is default, and random state is 42. For the same data, the random state is some number, which makes sure that you are getting same split if you pass the same number. Like if you're passing 42 on the same data again, you will get the same split. If you pass the same random state number as mine, you will get the same result for the same data. If you pass a different random state, you may not get the same results, but it does not mean your results are not correct. At this stage, I suggest please pass in the same test size and same random state so that you get the same results at the end. So let's run this cell so that we can get training and test datasets. Moving forward, let's check the head of, say, X train here, dot head, and here we have the training dataset. If you check test, and here it is for test dataset. I would rather call info on test and train dataset. So x_test dot info and run this cell, and here we have 167 entries in our test dataset. Let's copy this one, paste it here, and instead of test, train dataset. And if we run this cell, we have 339 entries. So after split, we are getting 33% in our training dataset, and the rest is in our train dataset. So now we are done with splitting test and train dataset. Let's move on to create and train the model. First thing first, we need linear regression model to train on our dataset. It's easy. Let's import linear model family from Scikit-learn so that we can use its member linear regression for our dataset. So we need to do another import here from Scikit-learn import linear model family. So we are going to import linear model family from Scikit-learn. Let's run this cell. Let's add few lines again. So the linear regression is a part of linear model family. Now we have imported the linear model family. Let's create an instance for linear regression model, which is a part of linear model family. So LM is going to be our instance linear model dot linear regression with capital L and capital R. Let's run this cell. So LM is our instance for linear regression here. If we write lm dot and press tab, we have a range of options that we can use. We want to use fit at the moment to train the model. So let's get this fit and pass in our training data set. If we press shift tab, so fit linear model, and X is our train data and Y is our target values. Let's pass in the training data set here, X train and Y train. Let's run this cell. So we got this output. It means our linear regression model has been trained on the provided data to the model. The most important thing is model evaluation. Our model is trained. We need to evaluate our model. Let's evaluate the model by checking its coefficients and how we can interpret them. Before coefficients, let's check the intercept. So lm dot intercept, you can press tab for autocomplete. Let's run this cell, and this is our intercept. The intercept, often labeled as constant, is the expected mean value of y when all x equal to 0. Let's move on and check the coefficients. We can get the coefficients with lm.coef. lm.coef. If we run this cell, this is the list of coefficients for all the given features to our dataset. We can create a data frame using columns from X as index and values of these coefficients in a new column called coefficient. It's organized and look better. Let's add few cells, and our columns are X dot columns. And if we run this cell, so these were our selected columns. What we can do, coef, and create a data frame pd dot data frame, pass in data is coefficients here, pass in index x dot columns, and columns, the name of our column is coefficients. So if we run this cell, so this index should be with small I, and if we run this cell and check coef, and here we have a better looking data frame with coefficients as a column and the feature names as index. Let's discuss coefficients briefly now. Let's consider this RM, which is room size, and 4.522. What this 4.522 means? This suggests if we keep all coefficients constant, a 1 unit increase in the room is associated with an increase in 4.52 in the price. The same is for other related coefficients. For example, the crime rate and the age decreases the price according to their coefficients, keeping all other constant. If you want further details and mathematics behind this, please read the suggested readings in the previous lecture. Let's move on and do the predictions from our model. We have trained our model, discussed the coefficients, which makes some sense. Now it's important to know how well the model is doing. So our model have never seen X test. Let's provide test data X test to our created model and see what the predictions are. Once we get the predictions from our model, we can compare them with what we have in our Y test. Let's get the predictions in pred, and we can call lm.predict and pass in X test. And let's run this cell. So we got the predictions for the test data in pred from our trained model. We already know the price of all the homes with features in X test, which is in Y test. Let's plot Y test and predictions as a scatter plot to see how they are related. So let's add few cells and plt dot scatter and pass in Y test and pred. If we run this cell, here we have a scatter plot. Along x-axis we have the test values, along y-axis we have the predicted values. It's even better to get a residual histogram that will tell us how much the predicted values differ from the test values. We can simply do this by subtracting the predictions from y-test. We can use SNS dist plot here. So SNS dot dist plot and pass in y-test and subtract our predictions which are in pred and run this cell. And here we have. So this residual plot doesn't look very bad. So moving forward, let's talk about regression evaluation matrix. To discuss regression evaluation matrices, I will go back to the reference notebook. And here we have some formulas and some definitions on the evaluation matrices. There are three common evaluation matrices for regression problem. All of these are loss functions because we want to minimize them. If we consider y is a vector of n predictions generated from a sample of n data points on all variables, and y hat is the vector for observed values, which are target values of the variable being predicted, the three evaluation matrices would be mean absolute error is the mean of the absolute value of the error. It is the average error, and we can calculate using this formula. Mean squared error is the mean of squared error. This MSE or mean squared error is more popular than MAE, which is mean absolute error, because MSE punishes larger errors, which tends to be useful in the real world. And we can calculate this using the formula provided in the reference notebook. The third one is root mean squared error, RMSE. This is the square root of the mean of the squared error. RMSE is even more popular than MSE because RMSE is interpretable in the Y units. RMSE is a frequently used measure of the differences between values predicted by the model and the values actually observed. RMSD represents the sample standard deviation of the differences between predicted values and the observed values. So we can calculate RMSE using this formula given in the reference notebook. If you want to explore and read more about these mean absolute, mean square, and root mean squared errors, you can follow the provided links in the reference notebook. Let's move on to the working notebook and calculate MAE, MSE, and RMSE for our model. For this purpose, we need to pass the y-test and predictions to the respective methods. Scikit-learn conveniently provides a way to calculate all these errors. To do this, we need to do another import. So from sklearn import matrices. Mean absolute error and mean squared error are the part of matrices, whereas RMSE can be calculated by passing the mean squared error to the square root function using NumPy. Let's calculate all these three matrices. Matrix dot mean absolute error and pass in test and pred, our predictions. Matrix dot mean squared error and pass in y-test and pred. And the third one is copy this one and pass into np dot square root. Let's pass them to the print function. And print here. So just to see what value is for what error, this one is MAE and the second one is MSE and the third one is RMSE, root mean squared error. Let's run this cell, and here we have MAE, mean absolute error, mean squared error, and RMSE, root mean squared error. So we're done with our very first machine learning project using linear regression model. Let's have a quick overview on what we did. We imported pandas, NumPy, matplotlib, and seaborn. Then we got a dataset from Scikit built-in dataset repository, created a data frame here, did some exploratory data analysis, and then we moved on to the machine learning section, where we separate the features in X and the predicted price or the target values in Y. Then we did the train test split. We passed in test size, which is default 0.33 and random state 42. Then we moved on and imported the linear model family from Scikit-learn and created its instance. Then we did the fit on our train data and got the fitted linear regression model. Then we checked the coefficients, and moving forward, we got the predictions from our test data. Then we plotted the distribution plot for our residuals, which is x-test minus predictions, and we calculated the evaluation matrices. So this was all about the linear regression model at the moment. I hope you enjoyed this lecture. Please go through this lecture once again and try to understand each and every step before you move on to the next lecture, which is the project exercise on linear model. You can repeat the model using all features in the Boston housing dataset and compare the differences with the results in this notebook. Try setting different random state and see how the results changes. You can also repeat this model with another dataset, kc_house_data.csv, which is provided in the course material. That dataset is on house sale in Kings County, USA. This is also a real dataset. Let's move on to the exercise project in the next lecture now. See you in the next lecture. Good luck.